Ever wondered, what happens when an earthquake's vibrations hit a layer of rock that's just the right speed?
It's a fascinating point, point of singularity, actually. The math gets really interesting.
Singularity? Sounds intense. Is this like a black hole for seismic waves?
Not quite a black hole, but a point where our usual equations, well, they kind of break down. It's all about critical modes.
Critical mode? Sounds like we're about to get into some serious earthquake science. So this paper dives into wave propagation in layered rock, right? The classic problem.
Exactly. We usually model the Earth as layers of rock with different properties. Seismic waves bounce and transmit through these layers.
And we use normal modes to describe these waves, like the familiar Rayleigh waves.
Right. Rayleigh waves decay exponentially with depth. But what happens when the wave speed matches the speed of a layer?
That's where things get weird, right? We get these critical modes.
Yes, the phase velocity of the wave matches the p or s wave velocity in a layer. It's a singularity in our usual equations.
So our normal equations for normal and leaky modes don't work anymore?
Precisely. Normal modes are trapped, leaky modes escape into deeper layers, critical modes are somewhere in between, yeah.
How do we even solve this problem? This paper uses the GRT method, I see.
The GRT method is a powerful tool for analyzing wave propagation in layered media. It handles reflections and transmissions at each interface.
So it's like tracing the wave's journey through the layers.
Exactly. It uses reflection and transmission coefficients to track the wave's energy.
But the GRT method also has problems with these critical modes, right?
Yes, the standard GRT equations become singular. The paper introduces a linear solution to fix this.
A linear solution? Instead of the usual trigonometric or exponential functions.
Yes, when the wave speed matches a layer, the amplitude changes linearly with depth.
So what do we learn about the eigenvalues and eigendisplacements of these critical modes?
The eigenvalues tell us the wave's frequency and wave number. The eigendisplacements show how the ground moves.
And how do they differ from normal modes?
In normal modes, the displacement decays with depth. In critical modes, it can remain constant, especially in the bottom half space.
The paper uses numerical simulations, right, to test these ideas?
Yes, they tested different layered models, homogeneous half space, increasing velocity models, and a model with a no velocity layer.
And what did they find?
The simulations confirmed the theoretical predictions. Critical modes show unique eigendisplacement patterns.
What about a simple homogeneous half space? Does that have critical modes?
Surprisingly, yes. For SH waves, shear waves, there's a non-dispersive critical mode where the displacement is constant with depth.
Constant displacement? That's unusual.
It's a special case. The wave propagates horizontally at the S wave speed.
What about models with increasing velocity with depth?
In these models, critical modes appear at the boundaries between normal and leaky modes. The eigendisplacements show interesting behavior.
Like what?
The displacement in the bottom half space becomes constant for the critical mode where the phase velocity equals the S-wave velocity of the half space.
And what about models with a low velocity layer?
These are more complex. The high frequency limit of the fundamental mode is determined by the low velocity layer.
So the low velocity layer dominates the wave behavior at high frequencies?
Yes, and the critical modes show energy concentrated in the low velocity layer.
What about the zero frequency case? That's a bit strange.
At zero frequency, the wave becomes a static displacement field. It's a limiting case.
So it's like a snapshot of the ground's deformation?
Exactly. The critical modes help us understand the behavior at this limit.
So what are the implications of all this for seismic imaging?
Understanding critical modes helps improve surface wave inversion. It reduces mode misidentification and missing modes.
So it leads to more accurate images of the Earth's subsurface?
Precisely. It also helps interpret 3D array data and understand the relationship between modes and ray paths. This research really bridges the gap between theoretical wave propagation and practical seismic imaging. It's a significant contribution to the field.
That was a great discussion. Thanks for sharing your expertise.